Assalamu alaikum, dear students. Welcome to the lecture of the classical mechanics. In this lecture, we will discuss the solution for the problem number 7.29. In this, consider the pendulum described in problem 7.15. We first look at the problem number 7.15, which says that a pendulum consists of mass m suspended by a massless spring with unextended length b and spring constant k. Find the Lagrange equation of motion. So this was the question number 15. So the pendulum's point of support rises vertically with constant acceleration a. Then we have to use the Lagrangian method to find the equation of motion. In the second part, determine the Hamiltonian and Hamilton's equation of motions, and then what is the period of small oscillation. So these are the requirements of the question we have to find. Let's go to solution. In this is the diagram for the question. Simple pendulum attached with the mass and with spring, and this whole spring pendulum system along with the support. This is the support of this system, and it is accelerating upward with acceleration a. So the very first thing, b is the unextended length of the spring when the spring is unextended, and L is the variable length of the spring when the spring is elongated, so its length will be L, variable length of spring. The very first thing, because we have one particle, so just and it's two dimensions, so two generalized coordinates x and y will be enough to describe it. So if we resolve this x component into an x, its motion or its coordinate into a corresponding component, so x will be equal to L sine of theta, and y will be equal to, because along the y direction we will be have y will be equal to L cos theta. This is this component will be L sine theta in front of theta, and this will be in direction of y will be equal to cos theta. So y is equal to L cos theta, and you know that this particle is moving with acceleration a, so further y displacement will be equal to y is equal to 1 by 2 a t square plus vit. If at time t is equal to 0 or its velocity is 0, it means when at the start its initial velocity will be 0, then it will start to accelerate. So y will be equal to 1 by 2 at square plus and this motion. So if we consider this origin, so below the origin we will be minus sign, so y is equal to minus L cos theta, and upward y will be equal to plus 1 by 2 at square minus L cos theta. Thus we have find the x and the y coordinate for this system by resolving this length into two components, x which is L sine theta, because this is in the front of theta, so that will be equal to L sine theta, and the y which will be equal to L cos theta, and plus this vertical distance which is covered, which is equal to 1 by 2 at square, above the origin 1 plus and below the origin minus L cos theta. Okay, we will be need x dot and y dot. As you know that kinetic energy is equal to m over 2 x dot square plus y dot square. So taking time derivative of this x and y, this will give us x dot is equal to this and y dot is equal to this. This is a very simple calculation you can do. Putting value of x dot and y dot in this expression, and further for potential energy, you know that potential energy is equal to mgy plus spring potential energy, elastic potential energy, which is equal to k over 2 and x square, k over 2 and x square. X square is equal to total length is L minus b. So L minus b will be effective, because L is variable length, extended length minus original length. So the change in length will be L minus b. So potential energy will be equal to k over 2 and x square. X is L minus b. Total change in the length. mgy plus this is the total potential energy due to position for gravitation and spring potential energy. Okay, the sum of the two potential energy. Lagrangian will be equal to T minus U. Okay, at this point we will be just put the value of this T and U in this equation. So our Lagrange will become m over 2 L dot square plus L square theta dot square plus A square T square, and this whole term and this whole term. So this is our Lagrangian. So further we can find Lagrange equation by putting this Lagrange function into Lagrange equation, which will give us Lagrange equation like for L we will have this equation, and for theta we will have this equation. Okay, because we know that for L we can write Lagrange equation d over dt partial L over partial L dot minus partial L over partial L is equal to 0. By putting that Lagrangian into this equation, so this term will go to 0 and we will left with this. And similarly for theta, d over dt partial L over partial theta dot minus partial L over partial theta. This will give this equation. Upon simplifying this equation of motion reduced to, if we simplify this equation and separating the variable, so this will give L double dot minus L theta plus minus A plus G cos theta is equal to this, and theta double dot is equal to this. Further, we have to find the Hamilton equation of motion. For this, we will need generalized momenta. Generalized momentum for PL and P theta, then we will substitute into this equation. So PL will be equal to partial L over partial L dot, which is this, and from this equation we can find the value of this L dot. Similarly, for P theta will be partial L partial theta dot, and we can find the value of this theta dot will be this. Okay, now H is equal to sum of Hamiltonian is equal to, because generalized Hamiltonian equation is H is equal to PIQ dot minus L. So we will PL L dot plus P theta into theta dot minus L. You know that at this point we have L dot and similarly theta dot. Just plugging value of L dot and theta dot in this equation and the value of Lagrange as we have previously found in this will give us the value of the Hamiltonian, this whole function. Okay, so this is our Hamilton equation. Hamiltonians are the total energy. We know that this expression contains the time term, so our Hamiltonian and total energy is not equal. At this point our Hamiltonian is this, and this contains time term, so our energy will not remain conserved. As time goes on, energy will be decreased. This is the Hamiltonians. For further we see that for the Hamiltonian equation for theta dot will be equal to partial H over partial P theta. So we can just plug the value of H and differentiate it back to P theta, and this will similarly for L dot we can find partial H over partial PL, which will be equal to this. Okay, the equation for PL dot and P theta dot can be found. PL dot will be equal to minus partial H over partial L. Okay, just plugging the value of H here and differentiating with respect to L. Similarly for PL dot, if we rearrange this equation by taking these term on the other side and equating equal to 0, we can write in more simplest and beautiful form. This PL dot, this all term will go to on the other side, so it will be equal to this. And similarly P theta dot is equal to minus partial H over partial theta. So plugging the value of that Hamiltonian and differentiate with respect to theta and rearranging by taking these terms on the other side, so P theta dot minus AT over L P theta, this whole term will be come out equal to this. And then for further, if I look back to the requirement of the question, Then we, in the last, we have to find what is the period of small oscillation. It means we have to make some assumption to generalize, use some approximation to find the oscillation, small oscillation, the time period of the small oscillation. So for third part, we can go back and see the solution for the problem number, part number C. I think this is part C. So we will use some approximation. You know that if we use the approximation sign, you know that sine theta is equal to theta minus theta cube over 3 factorial plus theta 5 over 5 factorial, ignoring higher order terms. So sine theta will be equal to theta, and similarly cos theta is equal to 1 minus theta square over 2 plus theta 4 over 4 factorial, ignoring higher order terms. So we'll pick some first term. So sine theta is equal to theta and cos theta is 1 minus theta square over 2. Substituting into Lagrange equation of motion, by putting the value of these terms, sine theta is equal to theta and cos theta is equal to 1 minus theta square. So that will give us these changes, because if we put the value of sine theta and cos theta into that functions, this will give L double dot minus this. Then from that we can find the value of theta double dot. For small oscillation, theta will be very less than 1 and theta dot will be also 1 and L dot will be also 1. Dropping all the second order terms, we'll give L double dot plus K over M L minus A plus G into this. We can drop the higher order or these terms, and this will lead to this. This is the simple harmonic. You know that we can compare this equation with minus omega square theta. So this is just like omega square, and you know that time period is equal to 2 pi over omega. So this is omega square. Omega will be equal to under root L over A plus G. So the solution to the equation for L will be equal to L is equal to L homogeneous plus non-homogeneous part. So any second order differential equation contain the solution for the two part, for the particular part and for the homogeneous part. Our second order differential equation is this one for the first part and for the second part. So we can solve this differential equation for the first part and for the second part. If we solve this equation, we know that L will be equal to L homogeneous plus L particular. So for both, this is the solution for the homogeneous part, this is solution for the particular part. So for L, our time period will be equal to 2 pi over omega, and omega is equal to K over M. So this is the total time period for L. So I will stop at this point and meet in the next lecture.